Okay, so let's pick up where we left off. So the last thing I did is I gave you a list of all imaginary quadratic HFDs, at least what their what the D is that they correspond. There's only thing like many. So we're going to delve a little bit deeper into this. First, I'm going to give you this. I can do this here. So Theorem, my notes you'll find this as there's some terminology in here that I'm going to have to explain a little bit. So, but I'm going to go ahead and give you the statement of the theorem.
That kind of off topic question. Is that Minkowski space-time Minkowski?
Back one.
Okay.
See, back then those dudes did all the stuff. Now it's impossible. Course, remove algebraic integer, of course you feel okay. Suppose K over Q is N, which equals of course you know that this is a ring of algebraic integers. This extension must be finite. This can be broken down. There's a theorem that says this is R1 plus 2R2. Moment. If in any ideal class, so here's kind of the big bound thing. In any ideal class of R, there is an ideal norm of I is less than or equal to n factorial over n to the n times 4 over pi to the R2 power square root of the absolute value of the field discriminant. And we'll apply this in a moment. Let me kind of talk you into this. The discriminant is a number associated with an algebraic number field. there's a number of ways to use this, in particular, as a determinant particular matrix. And we might talk about this more in depth later, but for our applications for right now, really this is all you need. If in the case of a quadratic field, Q adjoined with the square root of D, the discriminant is D. If D is equivalent to 1 mod 4 and 4D, if D is equivalent to 2 or 3 mod. Like I said, this anybody that's interested, if we don't get to actually doing this in a more general field, I can show you how to compute it. But in particular, it is the you can compute it as a determinant of a particular matrix, for example, and it encodes some information about the field. And here's an important result, just to kind of show you the utility of the discriminant. And let me kind of remind you what that means. That means that PR what it means to be ramified is the PIs are assumed to be distinct prime ideals here. If at least one of these exponents is bigger than 1, we say that prime is ramified. And how can you tell if and only if P divides discriminant of K? You probably remember earlier in this class when we talked about, I mentioned earlier ramified primes, and I made the remark that only finitely many primes in any algebraic ring of integers ramify, right? Well, this is why, because to ramify, it has to divide the discriminant, and the discriminant only has finitely many primes dividing it. So what this says is in any ideal class of R, there is an ideal such that the norm of I is bounded by this. The proof of this requires some lattices, and when you see a pi in a number theory class, you know somebody somewhere did an integral, right? I mean, that's what happened there. I was actually kind of hoping to prove this, but there's too much other stuff I want to finish up. Well, let me apply this at least. Any questions? Yes.
Is there a way to prove this without doing a bunch of analytic computation?
The only proof I know of is that.
Okay.
So let me not say I'm not a Sith. I don't speak in terms of absolute. I don't want one right now. And what do I mean by this decomposition? This is another kind of important thing. Let me add to the discussion here. And I'm going to throw in another theorem because this is a good place to do it. And to for example, embeddings of this, there are two embeddings in this into complex numbers. No shocker there, that's the identity. And the other one, this is another embedding in the complex number, right? Doing its conjugate. Notice in this case, what happens is, and notice by Galois theory, this is a root of a polynomial, and the two roots of the minimal polynomial over Q have these two roots. And so those are the only embeddings because you have to take, and in fact, in this case, they're automorphisms, right? Because they're both still trapped inside of here. Here, two. Both embeddings are real here. If you look at the Gaussian integers, you get two complex conjugate embeddings here. And again, this is an automorphism. And finally, yeah. Here's one that's got a little bit more flavor to it, right? Notice that as a ring, this is generated over Z by the element cube root 2, right? So ask yourself this. If I'm gonna have a complex embedding, where can I take cube root 2? Well, actually, there's three places here. I can take this, I can take the cube root 2 to any three of the roots that are complex of x cubed minus 2. Here's one of them. Here's another one. And here's another one. Where here omega is -1 plus square root of -3/2. Primitive cube root again, right? And since this ring is generated over Z by the cube root of 2, once though I know that those are the possible destinations of the cube root of 2, those define all my embeddings. Notice, as opposed to the previous example, these are not automorphisms because two of these embeddings leave the ring, right? Only the identity is an automorphism. In this case, the degree of the extension R1 and R2. Yes.
In the Galois case, are you gonna have either R1 equals 0 or R2 equals 0, or can you have it mixed up?
No, you can have it mixed up, right? So for example, take the normal closure of this, right? So in the normal closure of this, you've got well, the field would be, in fact, I should have done this in terms of fields. I'm so attached to rings, I did it that way. But if you look at the field, Q adjoined with the cube root 2 and omega, that'll actually have 6 embeddings, which is the order of the Galois group. And there will be several of them that are, well, actually, in that case, what we have, yeah, that one can't be embedded into this. So, yeah, but let me try to, in the Galois case,
if you have like a,
Yeah, so in the Galois case, I guess that's right, isn't it?
right,
Because
the
if it's
polynomial
Galois,
splits,
then you're either contained in the reals or you're not, right? And if you're contained in the complex numbers, let me rephrase, if you're not contained in the real numbers, then every automorphism should be one-to-one and onto, so it can't be a real embedding, right? Kind of thing. So yeah, that's an interesting observation. Okay, other questions? And I can't resist, but so everybody okay with this example?
You're saying that because in the Galois case, every embedding is gonna be an automorphism, is that what you're saying? Why that's?
Yeah, that's right. Um, this is called Dirichlet's unit theorem. R is algebraic integers. So let's do a little fun exercise with this. If you have a if you have a ring of algebraic integers, one of the important questions that you guys may have sort of put together is what's the structure of the units? Well, what this says is the unit group is CU direct some number of copies of C. This is so free. Where CU is torsion elements of UR. And by the way, where the torsion elements of UR? What can anybody think about a colorful way to describe those?
The elements with the finite word. Roots of unity.
So the roots of unity. So these are the roots of unity of R. So here's a question for you. What describe the rings of algebraic integers where the unit group is finite? Okay, there's one.
Imaginary quadratic.
So let's pick that apart. You can have R1 equals 0 and R2 equals 1. And this is imaginary. Zero real embeddings, and you've got two complex embeddings. What's the other case? Notice since you're non-negative integers, so you only have one real embedding. What was that? Grant's answer, right? That's it. Right. So what happens, so we recover something from this, what happens in the real quadratic case? In the real quadratic case, what we have is, well, in the real quadratic, what's the CU gonna be? Plus or minus one, because they're real, right? The only roots of unity that are real are plus one, minus one. So basically, what's gonna happen in the real quadratic case right here is the units of R from the isomorphic to C2 for X sub Z. And so there's actually a single unit that generates that big Z part. It's called the fundamental unit, right? And this is what makes factorization actually go. The interplay of units makes it much harder. The imaginary quadratic case is unique in this regard. And here's another one. So for the imaginary quadratic case, or the units of R are isomorphic to Z2. Two exceptions. Anybody know what they are?
Going high.
Here, the roots of unity are generated by I. Right? What's the other exception?
Plus square root negative 3.
Now you have the primitive cube root of unity. And by the way, of course, the negative cube root of unity is 6 root of unity. Those are the biggest roots of unity that you can have contained in a quadratic field. So the quadratics are very interesting, right? They've all got very simple units, plus or minus one, that's it, except in these two bizarre cases. Okay, any questions on that? I'm down to use this. Let's do a couple of classical things. A lot of you have probably in early number theory classes at some point in your history, you probably proved that the Gaussian integers are Euclidean. I'm going to prove a couple of things are UFDs and something else. Example. First, let's see. I want to select the Minkowski bound on this. Here we have n equals 2. Right? N to the n. Oh, let's do that. Here R2 is, what is this one? It's 1. Good. R2 is 1, and what's the discriminant? It's -4. Because here, your D is -1, that's equivalent to 3 mod 4, so that's so it's -4. But like yes, we take the absolute value. So the Minkowski bound should be 2 factorial or 2 factorial over 2 to the 2 or pi to 1 square root of 4 I guess at the end of the day, that turns out to be, 4 pi, doesn't it? Which is, I don't know much, but it's less than 2. So every ideal class contains an ideal. That's 2. And the only ideal of norm 1 is the entire range, so. It's mm, in this case, again, we have n equals 2, R2 equals 1. This time. The discriminant here is a -3. And so notice that that's even tamer than this, right? So again, all the numbers are the same except it's a smaller in absolute value. Let me do a couple others here. This one. Here we have n equals 2 R1, R2 equals 1. Here, the discriminant is -8. Right, and I think that's that in my head, right? So here what we have is Minkowski bound. We just get shorter every time, doesn't it? This is 2 factorial over 2 to the 2, 4 over pi to the 1 power times square root of 8. And this comes out to be all right, so I'm gonna quit fooling around here. How about this one? Let's do a couple that have some teeth to it. Here's one that is a favorite of us all. Here. Um, the discriminant here, -5 is equivalent to 3-4. So the discriminant here is -20. So Minkowski bound in this case is and in this case, what we get is what I get is 2.8. certainly less than 3. Now, this of course still could be a UFD, right? But we know that it's not. So, how many ideal classes are there? Well, one ideal one, the entire range, right? Worst case scenario, how big could the class group be? Yeah, I agree with that assessment. Here's what could happen. The prime ideal or the prime 2 could split into 2 prime ideals. You have 2 separate ideal classes with that norm in it. So worst case scenario. If the principal class and 2 other non-principal classes. Maybe. Right. By the way, if this were cubic instead of quadratic, there could be 3 ideal classes. Because here's what happens. If you look at the ideal generated by 2, it's in by 5. Who could, number 1, remain prime? If that's the case, then there is no ideal of norm 2, because the ideal generated by 2 has norm 4, right? And if that happens, then that thing's a UFD, period. Number 2, and I don't care whether those 2 primes are different or not. Well, actually, I do care. P was P1, P2. What's the norm of P1? That's the other thing that could happen. And this paints my worst case scenario. I could have a class for principals, 1 for P1 and 1 for P2. And that's the worst case scenario. Now, the first thing I notice is P does not remain prime, or I'm sorry, 2. In fact, there's a zillion ways you can do this. But it's not prime because it divides that product without dividing either one. So that means that the 2 must divide down into smaller primes. We also know the 2 can't divide down into 2 principal primes, right? Because in this ring, the norm of a plus b radical -5 is a squared plus 5b squared. So when 2 breaks down, it can't be principal, right? And in fact, we have shown earlier y'all remember doing these kind of computations, right? And this actually tells me class numbers too. Can somebody tell me why?
Because you don't have 2 products that are all.
That's right. That means that 2 equals p squared. So P and P are in the same class. And what is more, this computation over here shows that we square P as principal. So in this case, we have CL. Well, not with that. Five group size more. So right there, that's proof that that ring is a half factorial domain. Because the Minkowski bound shows that the class members too, and Carlos's theorem shows it's got to be a HFD. Right? Here's one with a little bit more meat on it. Yes.
What do you index for what are in the same class?
P in itself are in the same class. Because I said in the worst case scenario, what could happen is two might be P1 and P2, and they might be in different classes. But this actually is P squared. These two are the same. So whatever ideal class P1 goes in, P2 has to go in. Right? Because it's the same ideal. Let's do one that was a little more interesting. Example. And I think this will answer some questions that were asked earlier. If you look at this is where we got that exotic factorization. 81 is 3 to the 4th. It's 5 plus 2 radical negative 14, 5 minus. Right? So let's do the Minkowski bound. Here, N is 2, again, R2 is 1. Okay, I'll describe that. No, this is equivalent to 2 mod. So the square is minus 56. So the Minkowski down here is 2 factorial 2 squared times 4 pi. Like that. So it looks to me like that is I get about 4.7. Okay, so we've got our work cut out a little bit more for it, right? How many ideal classes can we have here? Well, okay. 2. Those 2. So again, I'm not claiming this happens yet, but 2 could split into 2 different problems and go into 2 different ideal classes, right? Quadratics, that's what happens. The most is going to happen, you're going to split. You'll have 2 of norm 2. Norm 3. At most 2. Right? Norm 4. I think so, at most 2. Because what you can have is if 2 equals P1, well, actually, let's see, well, let's actually investigate 4. And by the way, norm 4 is the last case we have to investigate because 5 is beyond our Minkowski bound. So suppose it has to be a product of these primes norm two, right? Another thing that could happen is, of course, two itself could remain prime and that could have norm four, right? So let's kind of see what happens here. But to have a prime, you can't have a prime of norm four unless it's principal, right? So that would knock us back into the principal class anyway. Let's see what happens here. What's the status of two? And this will come on just A plus B. Minus this. Okay, so what's the status of the ideal journey by two? Yeah, it's not prime. Do you know how it breaks up?
Same.
It's actually this. Because the square of this ideal is 4. It's generated by those 3, right? So clearly 2 contains this. And because you have the greatest common divisor of 4 and 14 is 2, so you've got the other containment. All right. So notice this is a perfect square of a prime. So there is a non-trivial prime of order 2. So right. How about 3? Right, that's the next thing. What about norm 3? The ideal term by 3. Three breaks up into 2 prime ideals, both norm 3. Right. So norm 4 is not an issue. Right, because as it turns out, the only ideal of norm 4 is the ideal generated by 2. Right, and the ideal generated by 2 is principal. Right. Everybody okay with that? And in fact, it's not prime, there's a good prime in every class. So the worst case scenario is the principal class a class containing P and 2 classes containing 2. Let me do this. That's and actually we're done because this is exactly what happens, right? So we saw earlier that this is a class of order 4, so is this, and this is the class of order 2. So in this case, we recover effectively what we've done on our earlier example is we showed that there's a subgroup isomorphic to Z4. Now the Minkowski bound says, hey, that's it. That's all of it.
So from the beginning, if we know that 2 divides the discriminant, we can immediately go to
it was a square.
Well, that's right, right. I mean, you're using that term that we said because we know that it's ramified, right? You gotta be a little bit careful. So here's kind of a fun exercise. I'm gonna say this too. What if we have this one? Oh, I'm gonna say discriminant. Okay, so actually, I'll leave this as an exercise. See if you can figure out that one. What you're gonna have to figure out is the discriminant, which I'll tell you about later. Or you can look it up, but this one is actually UFD. All right, so see if you can get to the bottom of that. Okay, any questions on that? So now, at our fingertips now, we have, the ability to, in theory, check whether these things are UFDs or not, if you can give the discriminant and those other things. You go through in this kind of systematic way, and you can make these computations. But here's the question. For the UFD. One of the most interesting subroutines on the planet. Well, in the multiverse, actually. It's you tell me why there's no way this is going to be a UFD.
UFDs are integrated closed.
UFDs are infinitely close. It's impossible for this to be a UFD because this element right here is a primitive cube root of unity, and it's not in there. It can't be a UFD. So one might argue, what's the next best thing? This is actually an HFD, and we'll talk about that next time. In general, let me ask you this question here. Consider Z omega, where omega is equal to square root of D, if D is equivalent to 2, 3, 1, 4, and 1 plus radical D over 2, if D is equivalent to 1, 1, 4. So this is my catch-all for these things about integers. These are the only ones that are allowed to be UFDs because they're interval closed. N is here a natural number. The only way that this is interval closed is if it is 1. Right? So if n is bigger than 1, it's not possible for these animals to be UFDs. So if one were to argue that your next best thing is an HFD, which might be arguable, but if that's your next best thing, for what values omega and n, is this ever an HFD? There is only one value, right? Omega, well, actually, let me go a step further. D must be -3 and n must be 2. And that's it. For imaginary quadratics. That's it, right? For reals, they're probably all. But anyway, so we'll talk about this. This is kind of a theorem. And when I first proved this theorem, I actually used calculus at one point. And I was like, gosh, I just thought this paid for my, for my job. But, I actually used calculus. So anyway, y'all have a good weekend and I hope to see you at the math club. Other than that, I will see you on Monday.